Welcome back. In our introduction to differential equations, we looked at a simple population growth model. This population growth model told us that the time rate of change of a population n is proportional to itself, and that constant of proportionality was the growth rate r. The solution to this differential equation is what we termed exponential growth. But what we found is that this model is unconstrained. That means that the population keeps growing and growing with time. This is obviously not a very realistic model. The reason for this is that there is no mechanism embedded in the differential equation for the population to plateau or even decrease. So this leads us to the question, can we improve on this model? So let's modify the model as follows. Let's suggest that the time rate of change of a population is equal to our original model, Rn, but let's add a factor of k minus n over n. So k is what we call the maximum sustainable population. And that can be a population of bacteria or humans or whatever you might be dealing with. So therefore, let's introduce a new variable x, which is equal to the fraction of the maximum population, k. So if we divide by k, the above differential equation, it gives us a new differential equation that is a bit easier to deal with. And that is dx by dt is equal to rx 1 minus x. So this tells us that the time rate of change of the fraction of the population, so again a fraction will go from 0 to 1, is equal to the growth rate multiplied by the instantaneous fraction x, which is essentially our original model here, but we're adding an extra term here, 1 minus x. So before we dive in to solve this differential equation, let's see what this might look like. So at early times, x will be fairly small. So if x is fairly small, then 1 minus x is approximately equal to 1. And therefore, dx by dt is approximately equal to rx, which is simply our original differential equation. So for early times, what we actually have is exponential growth. But as x gets larger, and again, x can go from 0 to 1. So as x goes, let's just call it approximately 1, but really it can be 0.7, 0.8, whatever you might have. Then 1 minus x will be approximately equal to 0. And so what this does is that this bracketed term becomes smaller and smaller, thus it decreases the rate of change of x. So at early times we have exponential growth, but later on we no longer have that exponential growth. And we'll plot this later on in our solution. So as in the previous video, we're dealing with separable equations, and we can see that this equation is very easily separated. So we see we have this term here with the variable x, so we can bring it to the other side by dividing both sides of the equation by x 1 minus x. So let's go ahead and do that. That gives us 1 over x 1 minus x, and now what we're going to do is multiply both sides of the equation by dt, which gives us dx r dt. And we can go ahead and integrate this from an initial population x naught to an arbitrary population x, and similarly from time 0 to time t. So as mentioned, there are some really useful tools out there, such as Wolfram Alpha, or if you have access to Maple, you can usually solve these integrals fairly easily. Also, many integral tables will have integrals that are tabulated that are in the same form that you are dealing with. However, that might not always be the case. If we look at this integrand, we can separate it into a partial fraction. And setting it to a constant denominator, or the same denominator, gives us this. So again, to solve for these constants a and b, all we have to do is look at our left-hand side here and our right-hand side here and equate the constants and the variables. So equating the constants, we have 1 is equal to a plus b. And equating the variables, so here our variable is x, we'll have 0 on the left-hand side and minus a plus b. And I apologize, I made a mistake here. There is no b here for the constants. So we quickly see that solving the system, we have a is equal to 1 and b is equal to 1. Fairly straightforward. This allows us to carry through our integration. So we know that the integral of 1 over x is ln of x, and it's evaluated between x naught and x, so we have ln of x minus x naught. And here, the ln of 1 over 1 minus x will be the negative of ln of 1 minus x. So it's the negative of ln 1 minus x, and this is evaluated between x naught and x. And on the right-hand side, we just have the integral of r dt. We're assuming a constant growth rate. And again, this might not always be true. Sometimes we have a variable growth rate. These things happen. But anyway, so we'll have r multiplied by the integral of dt, which is just t. And here we have it. And I apologize, this should be ln of x minus ln of x naught. So when we have the difference of two natural logarithms, we can just express them in a fraction. And again, we have the difference of two natural logarithms, so we can set up another fraction, which will give us ln of x over x naught multiplied by 1 minus x naught over 1 minus x. And all of these is equal to RT. So again, I just remind you that what we are looking for is a closed form solution. X of t is equal to something. We can isolate x, which appears twice on the left-hand side, by taking the exponential of both sides. I will leave this to you to solve on your own. So the final solution here is x of t is equal to 1 over 1 plus 1 over x naught minus 1 multiplied by e to the negative rt. And this is our solution, and this is what we call logistic growth. So let's consider what this is telling us. For positive growth rates, when the time goes towards infinity, so that is for very large times, we have this exponential term over here. And this will become smaller and smaller. And what this leads us to is just a fraction 1 over 1. So we have x as t goes to infinity is equal to, or we'll just say is approximately 1. And that makes sense. So as time gets larger and larger, the population goes towards its maximum sustainable population. Let's consider the other case where we have a positive growth rate, but t is very small. So in the early stages of growth. So again, maybe you just placed bacteria in a petri dish, or there's a new settlement of a population of humans, let's say. So at early times t, what do we have? So we know that e to the power of 0 will be equal to 1. So all we have is 1 minus 1, so that's 0. So we see that x for t approximately equal to 0 is approximately equal to x naught, which is our original population. And that makes sense too. So let's have a look at what this might look like. So plotting x versus t, we have an initial population x naught. And again, the differential equation that we are solving is dx by dt is equal to rx 1 minus x. So for early times, x is fairly small. And therefore, this bracketed term here is approximately equal to 1. So in the early stages, we actually have more or less exponential growth, because our differential equation is more or less just equal to rx, which we found to give us exponential growth. But as t gets greater and greater, this bracketed term becomes smaller and smaller. And what this means is that our derivative, or our time rate of change, of the fraction of the population gets smaller. And so what we have is something that looks like this, which what we say is that it asymptotically goes towards its maximum sustainable population, where x is equal to 1. Now, this model is not perfect, but it's definitely better than our original population growth model. It does not extend to infinity as time gets larger and larger. It has an embedded mechanism to reduce the growth rate as the population increases. It's actually been shown to produce pretty good fits to actual population data over fairly small time spans. So this was a fairly realistic example of a population growth model which is described by a first-order nonlinear differential equation that can be solved by separation of variables.